All right, so this new approach is similar to undetermined coefficients, but we're going to call this one the annihilator approach. So to understand what the annihilator approach is, we have to understand a couple of basic concepts first, and then we can put them together with how that helps us figure out the undetermined coefficients. So the first underlying concept we need to make sure we're clear on is something called a factoring operator. And it kind of goes like this. When you're factoring something, you can rearrange the order of the terms for whatever reason. So in the past, it really hasn't mattered. Let me show what I'm talking about. So if I have d squared plus 5d plus 6 times y, I can factor the d squared into d. Let's see, now put a y there. Okay, so that's going to be a 3 and a 2 on that. That's actually equivalent because I've got essentially three things being multiplied. So I can swap the order around to d plus 2, d plus 3 times y. Okay, so what have we formally illustrated that? Is that if I'm looking at factors of something, I can rearrange them using the commutative property. So factors of linear differential operators with constant coefficients commute. All right, next concept is something called an annihilator operator. Get this scrolled up there. So if L is a differential operator with constant coefficients and f is sufficiently differentiable such that the linear operator of f of x equals 0, then L is said to be an annihilator of the function. Now, this is not a tremendously new concept for us. It's essentially, we're looking at what derivative would cancel something out so that there's nothing there. So, for example, if I have a constant function, if I just take the derivative of that, so if I do the derivative of y, the derivative of k, and the derivative of a constant would be 0. If I take, say, in y equals x, how many derivatives do I have to take in order for that thing to be 0? So if I take the first derivative, I get the derivative of x is 1. So if I take the second derivative, then that derivative would be 0. So this has got an annihilator of 2, degree 2. Okay. And then similarly, how many derivatives do I have to take on x squared in order to get it to cancel out? So since it's a degree 2, I want to take one more than the given degree. So that's a third derivative. Okay. So a polynomial can be annihilated by finding an operator that annihilates the highest power of x. The functions that are annihilated by the linear nth order differential operator are simply those functions that can be obtained from the general solution of the homogeneous differential equations. Okay, so we're dealing with a polynomial, just a polynomial, just look at the highest exponent. What about interesting situations? So what about something like this, where it's e to the alpha x, x e to the alpha x, x squared e to the alpha, how would we, what's a derivative or differential operator that could essentially cancel that out? And that's just us being a little clever with how we're multiplying terms out. So if I take d minus alpha to the n y, that would actually cancel any expression of that general format out. So the alpha is just, again, the coefficient of the exponential expression. Sorry, I feel like I should also comment that the n goes back to the highest power of the polynomial component. And then what about more complicated things that look like this? So essentially patterns that have sine and cosine in them. And the differential operator in this case would be d squared minus 2 alpha d plus alpha squared plus beta squared, all of which to the nth power. So n again refers to the exponent of the polynomial. Alpha and beta are given in the pattern of the function.